Today's video is focusing on something called intermolecular forces, or sometimes abbreviated as just IMFs. This is one of those instances in science where it's something that is really a simple concept but sounds more complex than what it is. Just the word intermolecular sounds very like sciencey, but really what we're looking at are the forces of a molecule and then that prefix inter, which stands for between. So intermolecular forces are the forces of attraction, and this is the key part, between molecules. Okay, so we're not looking at what makes a hydrogen atom bonded to an oxygen atom. That's the bond, the covalent bond within the molecule. We're looking at the forces of attraction that connect one water molecule to another water molecule to a third water molecule and so on and so forth. Right? The attractive forces that keep certain things held together. And we have examples of things that have very strong intermolecular forces, like the molecules that make up a sample of concrete or the atoms that make up a steel bar. Those have really strong forces of attraction because at room temperature, they're solid and they're very rigid, very stable, sturdy solids. Compare that to something like water. These are molecules of H2O. At room temperature is a liquid, and so they have a pretty strong force of attraction, but they're able to kind of slip and flow past one another, which is why we can pour water from a pitcher into a bunch of glasses. And then we have examples of things that have really weak attractive forces, no attraction to themselves whatsoever, like the air that we're breathing right now. There's oxygen and nitrogen molecules floating around our atmosphere, and they don't really have that much of an attraction between themselves because they're really small molecules and they don't have several of these intermolecular forces that we're going to outline here next in our video. Okay, so we are going to use this not so much as a way to identify the forces, but to rationalize why some substances are solids, liquids, and gases based on their level of attraction, which really stems from the orientation and the build of the molecule. Okay, so we have three intermolecular forces that we're going to use to compare strength within a sample of molecules. The first one is our dispersion forces, and these are the weakest. And this one is based solely on the number of electrons. Okay, so if we're comparing how widely dispersed a sample of electrons are within a molecule, a substance that has very few overall valence electrons will have really weak dispersion forces compared to a substance that has a lot of electrons per molecule, where those electrons have a greater chance of attracting and kind of overlapping with one another. All right. The second force that we're going to talk about is called the dipole-dipole force. I'm going to refer to this as kind of like our medium strength because it's not quite as strong as hydrogen bonding, which is our strongest, but it's definitely stronger than our dispersion forces. So it kind of lands somewhere in between the three. Dipole-dipole is kind of an interesting term. Really, we're focusing on this concept called a pole. And if you think about like North Pole, South Pole, the magnetic poles of our planet, a dipole-dipole exists when you have a positive and a negative region within the molecule itself. And so really what this one is referring to is a sample that is asymmetrical. Okay, so a good example of something that has a dipole is this water molecule right here. We notice there's like a slight bend to the overall structure. Well, that's because remember that if we were to draw out the actual Lewis structure for water, we'd have those lone pairs and then two hydrogen atoms bonded to it. And so there's this kind of bend and this overall asymmetry in terms of one water molecule. So the fact that we've got this like large region of electrons up here and not so many down below due to its asymmetry is what causes it to have a dipole force. Okay? And the last intermolecular force has to do with hydrogen bonding, and it really is only when hydrogen is bonded to nitrogen, oxygen, or fluorine. Those three elements, when hydrogen is bonded to them, has such a overall difference in terms of the actual strength of their electron attraction that it causes this really strong intermolecular force between those elements. So whenever we see an example of a molecule where hydrogen and oxygen, or hydrogen and nitrogen, or hydrogen and fluorine are bonded together, they have really strong intermolecular forces. So the main thing that we're going to see a really common pattern of is hydrogen likes to bond really easy to carbon. This is not an example of an intermolecular force. Okay, so we'll see that happen quite a bit in chemistry, where hydrogen and carbon bond together. We refer to those as hydrocarbons. They just don't have as strong of an attractive force to qualify itself as a hydrogen bond. Okay. So the real true purpose to studying these intermolecular forces is it's our way of not only being able to differentiate things that are uh, solids, liquids, and gases at room temperature, but it also helps us to understand why certain things will melt at higher temperatures or lower temperatures, and same as boiling. And then these two other topics, vapor pressure and surface tension, what we refer to as physical properties that really identify the way that one substance behaves compared to another, right? So melting point refers to the temperature at which a substance melts, pretty straightforward. And then boiling point, again, is the temperature at which a substance boils. Okay, pretty straightforward concepts, but we also have to remember that not everything melts very easily. Like when we hear the word melting, the first thing that comes to our imagination is like an ice cube melting or ice cream melting, things that we have, pretty common occurrences of that we know of in terms of melting. But everything really can melt. If we overcome their intermolecular forces of attraction, we can get things that seemingly wouldn't melt easily to melt, like gold. When they want to make jewelry, they can heat up gold, which is a solid at room temperature, to a really high temperature and get it into the liquid state and then manipulate it much more easily into different forms and shapes to make jewelry. And then the same for boiling. Boiling usually is just something that is indicated as like you boil a pot of water. But really, boiling is whenever you take any liquid and turn it into a gas, and we can get anything with the right temperature to cause a liquid to go into the gas state. But what we're really doing is breaking up this level of attraction from one molecule to another. Vapor pressure is what I always refer to as the rate of evaporation. So, how quickly or how easily does an object evaporate or go from the liquid state to the gas state? Again, something like water, we know we can boil and convert into steam, but that takes a long time to get that done, depending on the size of it, and it takes a lot of energy to get that to happen. But there's examples of liquids that we know evaporate really easily. The best example that I always use is hand sanitizer. There's a liquid inside the hand sanitizer that we rub into our hands that not only helps kill bacteria, but does a really good job of evaporating just with the application of the heat from our hands, so we don't always have to then get paper towel or something like that to dry our hands off whenever we want to use it. So there are certain liquids that have really weak intermolecular forces and will evaporate at a much faster rate. And then some liquids have really fast or really strong intermolecular forces and therefore have a really slow rate of evaporation. Right? The last one is surface tension, and that is the force of attraction across the surface of a liquid. And the one example that I think appears in every single science textbook whenever they talk about surface tension is that water strider bug that can glide across the surface of the water. And that has to do with the specific feet that it has and its ability to spread the weight of its very lightweight body across the surface of its feet. And it reduces its overall pressure and can use the surface tension of water to be able to stride across the surface. So the actual concept of surface tension has to do with the fact that in a glass of water, if you visualize this as a glass of water, all the molecules that are down below have water molecules 360 degrees all the way around them that they could be attracted to. But across the surface of that liquid, the water molecules just have the other molecules that are directly adjacent underneath them to the left and to the right. There's nothing across the top. And so because there's less molecules for them to attract with across the surface, they have a greater force of attraction across that, again, surface of this glass of water, which causes water to always form this kind of nice domed shape across the top. That's why raindrops have this nice rounded shape whenever they fall. It has to do with the outer surface tension of water for this particular example. All right, so all of these are just examples of different physical properties that a molecule can have, and they can be greater or less than depending on their intermolecular forces. So the pattern here is pretty simple. The greater a molecule's IMFs, or intermolecular forces, the greater its physical properties. So if you have really strong forces of attraction molecule to molecule, you're going to have a really high melting point, meaning you have to apply more energy and more heat to melt that substance to overcome the really strong level of attraction. Same for boiling point, and then the greater their level of attraction, the slower their rate of evaporation. It's going to take a longer time for those substances to overcome their attractive forces to one another. And then again, the greater that level of attraction, the greater that surface tension is going to be across the surface of that liquid. Okay, so really what we're using this as a way for us to rationalize why one substance may have a greater or less boiling point, but we can also use this as a way for us to be able to identify the differences from one unknown to the other. And so if we use this example over to the right, we've got three different substances, A, B, and C, and A has relatively weak intermolecular forces because it only has dispersion, but substance B and substance C have increasing intermolecular forces. So substance C has the greatest intermolecular forces because it has all three different types. Then that means that substance C also has the greatest physical properties. So in terms of the highest boiling point, substance C by far is going to require the greatest overall energy to overcome that force of attraction and turn this liquid into a gas or to boil it. Oops, I keep missing the camera there. All right, which one of these is going to evaporate the fastest? Well, this one again is that opposite concept. If substance A only has dispersion forces, then they have really weak forces of attraction molecule to molecule. So then it doesn't really require much energy for those forces to be overcome, and therefore substance A will evaporate pretty quickly.